Great. Well, thanks for having me here. It's been a great visit. It's been a long time since I've been to Ann Arbor. Thanks for delaying your weekend to hear a talk. I'm going to try not to make it too technical. So hopefully it'll be more interesting. And in fact, a lot of the conversations I had today kind of were around less about the technical aspects of what we did in the AMPLab and more around sort of how the AMPLab was built and run. So I'm going to try to cover a little bit of both, but feel free to ask questions and interrupt me and whatever. I'm looking, yeah, okay. And I guess I'll talk, if I have time at the end, a little bit about what we're trying to do at Chicago and why I'm there and why I hope some of you, as you're finishing up your degrees and you're thinking of places to apply for faculty jobs, you know, take a look at what we're up to at Chicago. So let me get started. So, you know, kind of AMPLab, as Jack mentioned, you know, played a pretty large role, I think, in kind of the evolution of the open source big data ecosystem. This is a chart I found online that talks about Apache Hadoop, and it goes back to 2006 when Doug Cutting and some other guy, I can't remember his name, Mike Caffarella, who's not at the talk, built this thing called Hadoop. If you kind of build this out this way, you'd see a few other things. So in particular, Google and some other big web companies, but in large part Google, were building a lot of their own infrastructure to handle large amounts of data. They felt that the existing database systems either couldn't scale to the way they wanted, or they would be too expensive if they tried. So kind of out here is Google building a bunch of infrastructure, in particular the MapReduce system for parallel processing. If you go out this way, to grumpy old database folks like Jog and myself, there was actually this whole area of massively parallel database systems that pioneered a lot of the techniques that get used for taking large data sets, spreading them across large clusters and running queries. I know you had Mike Stonebreaker here earlier in the week or last week. You know, Mike famously raised some questions about whether the MapReduce movement was a good thing or a bad thing. You know, well, you know, I think that question's been answered. But anyway, if you go forward, so you know, open source Hadoop came out in 2006. And then there was this explosion of new systems being added to do all sorts of things, whether it was stream processing, you know, graph processing, you know, SQL query processing, ETL, you name it, right? And things just keep getting added and added to the stack. Spark kind of showed up on the consciousness of Apache around 2012. But it was actually grew out of a project that we started in Berkeley before the AMPLab called the RAD Lab. RAD stands for Reliable, Adaptive, and Distributed Computing. And it started off, basically the goal was to build self-managing clusters and self-managing systems. And the insight that they had, and I actually wasn't, I was doing some other stuff at the time. I was off doing stream query processing. But when the RAD Lab started, what they were trying to do was, they said, all right, if we want to build self-managing data centers, let's say, data centers are really complex. We're going to need machine learning to you know, watch all the telemetry that's coming off the machines, build models, and then do predictions so they can then adjust what's going on in the machines. But since those systems are so complex, we probably can't do it just by you know, taking an operating systems graduate student and giving them the Introduction to Machine Learning book, right? Maybe what we should do is get some people who work on the cutting edge of machine learning, put them together with people that are building these cutting edge computer systems, and then together try to solve this problem of self-managing systems, okay? So it was a pretty good idea, and you know, around 2006, they put together a group of people from these different areas to attack that problem. And towards the end of that, one of the things that sort of bubbled up towards the end of the RAD Lab was this system called Spark. And you'll notice there's a lot of connections here with this talk. And so you notice this guy here, took a break from some of his networking work to do Spark. Oh, wow, Musharraf can tell me if this is a true story or not. Here's the way I heard the story. The way I heard the story is that, so we had machine learning and systems people sitting together. The machine learning people were trying to scale up some of their algorithms. They took Hadoop. They tried to run their algorithms on Hadoop. They ran horribly in terms of speed. They were really slow. So they walked over to Micheal and Musharraf and some of the other systems people in the lab, and they said, hey, do you mind helping us debug our machine learning programs, because we're running them on this cutting edge parallel infrastructure and it's really slow. And they looked at the code, they saw what was going on, and they said, hey, you know what, actually it's not a bug. What's happening is you're trying to use Hadoop for something that it's really not good at. And in particular, what they were trying to do is they were running iterative machine learning algorithms where you read in a data set, you process it, you come up with some model, but then you iterate over that data to refine the model. And the way that Hadoop was set up, and we'll talk about this in a few minutes, and again, since Caffarello didn't come to the talk, I can say whatever I want. Basically, between every iteration, it had no memory, no recollection of what it had brought into memory and where it put it. So it would read it all in from disk again. Right? So you're basically, every time you iterate over the data, you're starting from scratch, and it goes really slowly. So part of the motivation behind Spark was to solve that problem and say, okay, let's build a scale-out computing engine that can be smarter about how it manages memory and can preserve that knowledge across multiple parts of the program, and then that way get rid of a lot of those inefficiencies. And the reason I tell this, it's kind of a long story, but the reason I tell it is because it's part of a theme that I'm going to revisit a few times. That happened because we had a group of machine learning people who felt very comfortable walking, not across the hall or to a different building, but over to the next desk and asking somebody who's working on computing systems, to help out. And it's that kind of close collaboration that's been the hallmark of these types of projects that have been set up at Berkeley over the years, RadLab being one. And then when the RadLab wound down, this other thing we started up called the AMPLab, which is what I'm really going to talk about for the rest of the talk, for most of the rest of the talk. So, towards the end of this project, a bunch of us, some people were working on scalable machine learning, so they saw kind of big data happening from that point of view. Me and Scott and Jan were all off taking industrial leaves, doing startup companies of various types. And because of that, sort of became aware of what was going on in industry in terms of the huge volumes of data that people were starting to collect and the difficulty that those people were having extracting any value out of that data. So when we all got back from our various leaves and Spark started up, we looked and we said, okay, the next big thing should be what's now called big data analytics. But at the time, we kind of were calling it scalable machine learning and things like that. Okay, so that's kind of how that happened. The other thing I just want to mention is this explosion of innovation and an explosion of different systems really was enabled by the open source software movement. So people all around the world were able to create all these different systems and get some amount of traction with them. There's some good things and some bad things about this, right? There's lots of innovation. On the other hand, if you're a company and you're trying to figure out, hey, what's the latest, greatest big data stack that I should use to solve my problem? Well, you've got a real nightmare here because there's so many different systems. They have overlapping functionality. They weren't meant to work together. The chances of any one of them solving your problem is basically zero. So from an industrial point of view, from a production point of view, all this innovation is great, but it's kind of unwieldy and it's hard to work with. Okay, so on the good side, open source, let 1,000 flowers bloom. On the bad side, it's kind of chaotic, and industry in general doesn't like chaos. Okay, so good. So that'll be another theme. All right. So we started working on Spark. The initial release, I think, was 2009. Very quickly, we started getting a lot of interest in it, and some of the students in the project got an interest in really building a community. So they said, hey, we're getting so much interest in this software that we kind of just threw out into the world. Why don't we do the extra work? They were probably encouraged by some of the faculty, but why don't we do the extra work, make sure it really works, make sure people can use it, and then let's go out and do some evangelism. Let's actually build a community. So we started a meetup group, if you're familiar with meetup.com, about Spark. None of us, I don't think, were forward-looking enough to remember to take a snapshot of this picture back when we had the first meetup. So this was a couple months later. This was the oldest one I could find on the Wayback Machine. But at the time, early 2013, so a little over, almost not even 4 years ago, we had one group in the world with a little over 500 members. Then a bunch of weird things started happening. So you start seeing articles like this. I always show this article when I give a talk at a university because it gets faculty really nervous. And basically what it says is, so the O'Reilly guys did a study where they looked at job offers, job openings, they looked at salaries, they did a textual analysis to figure out which skills correlated with higher amounts of money. And they found, when they did this a year ago, that Spark was the #1 thing that you could put on your resume to make more money as a data scientist if you said you knew Spark. And if you said you had a Ph.D., it gave you a bump, but not as much as if you said you knew Spark. So, for those students in the audience, put down your books, start learning, ask Micheal how Spark works. No, but anyway. So, and that's just, it's a fun, kind of crazy example. This is less crazy, but, Spark became super popular, and it became, and I think it still is, the most active open source project in this whole big data menagerie. So if you look last night at about 11 o'clock to see how many meetup groups there are now. So in 2013, we had 549 members. We now, as of yesterday, have 549 groups around the world with over 250,000 people that are willing to at least sign up on a web page that says, yes, I'm willing to go to meetings with people who talk about Spark. So, thinking about this as a graduate student research project, that's just phenomenal, impact. And so, I want to talk a little bit about how that happened. All right, so the AMPLab, as I said, was kind of this next generation of this Berkeley shared lab thing that we'd been doing for a while. At its height, it was probably about 90 to 100 people involved. And these people were from systems, from machine learning, and here, I'll just build this out. We were able to do something I think that was pretty interesting, which is when we started the project, we weren't sure that it was the kind of thing that the NSF and other government agencies would fund. So we went out to companies, and we went to Google first, SAP next, IBM, Amazon, and we told them what we were thinking of doing, and we asked them if they would be willing to contribute some funding to help this along, and those companies agreed, as did, at the end of the day, 30 or so others. And so this is kind of a snapshot of the sponsors at a certain time. But given that head start, we were then able to apply for this National Science Expeditions Award, which is one of these big 5-year, multi-million-dollar awards that they give a very few of, and we were able to get that. So the project had this really nice funding profile where about half the money was coming from the kind of grants that we usually get, and about half was this very flexible funding that was coming from companies who were interested in the work and interested, of course, in meeting the students. And as the software got more and more popular, we're actually interested in being in on the activities around the software and figuring out new directions for the project. So it ended up being a great environment in terms of resources, but also, and I'll talk about this again towards the end, we would meet with these companies 2 or 3 times a year. and all the students at every meeting would get up and present their work. They would get detailed feedback from people at these companies who were interested in what they were doing. And so we got, this leads to internships, this leads to joint projects, and it leads to very immediate and useful feedback in terms of the direction of the project. So in particular, if you're a student and you're working on, say, networking, and you say, hey, I want to solve this networking problem in data centers, you could talk to people at these companies and they'll tell you, oh yeah, well, you know what, that's actually not really a problem in data centers for this reason or that reason. Or they might say, well, that is a problem, but not for the reason you think, it's because of this other thing. And that type of feedback is invaluable. So, now that I've moved out of the kind of the Berkeley, envelope that's good at doing these things, I mean, it's going to be interesting to see about building that kind of thing. I know you guys have a lot of industrial engagement as well, but it's just for this particular project, it was super valuable. All right, so great. So what did we pitch these companies? What did we actually say we were going to do? Well, the idea was you want to make sense of big data. So what do you have available to do that? And the idea was you have three resources: algorithms, machines, and people. That's where the name comes from. So algorithms, think about machine learning, statistical processing, and so on. Machines, we were thinking about large clusters, data centers, scale computing, clouds, and so on. And then people, our initial view was we were going to use things like Mechanical Turk and other connected types of systems like that to allow people to participate in the analytics. And the idea initially was that, using machine learning on scalable machines will get you a certain amount of accuracy and will solve a certain class of problems. But there'll be other things that the algorithms aren't up to do yet. And that's when you bring in people, right? Because there are certain things that people are good at, certain things that algorithms are good at. If you build that hybrid system, you'll be able to solve much more of the analytics problem. Okay, and so the pitch was, let's build a system that integrates these three very different types of resources to solve analytics problems. Okay, and that's what AMP stands for. Okay, so what did we end up doing? We ended up building this thing called the Berkeley Data Analytics Stack. The acronym is BDAS. It's pronounced?
It's called BDAS.
It's called BDAS. Thank you. I'm glad you said it, not me. But it's called BDAS. I built it this way because that's a good way to think of the stack. At the bottom, there's this virtualization layer called Mesos that allows you to take a physical cluster and partition it into smaller clusters. That actually was something that grew out of the RAD lab as well as Spark. There's a storage layer. Alluxio is a system that used to be called Tachyon until a company that had a product called Tachyon had their lawyers send us a friendly note that we needed to change the name. Succinct is a more recent project that basically does compressed storage and allows you to do queries on the compressed stuff without having to uncompress it. Above that are two processing engines. Spark, which we're going to talk about in a little more detail, that's that extended version of MapReduce for doing iterative processing. And something called Velox, which is kind of undergoing a name change now, which is focused on serving machine learning models. So Spark is for building the models. Once you've built the model, you now want to deploy it in an application. That's what Velox is intended for. And then on top of that are all these different systems that were built to allow people to do different types of analytics. So, there's a SQL engine, there's a streaming engine, there's an R interface for statistical processing, machine learning, graphs, approximate query processing, data cleaning. These are all things that are built on top of the rest of the stack. And the way I like to explain it is each one of these white boxes is basically somebody's Ph.D. thesis, right? Maybe a couple people, but this is all student-generated code and student-generated systems that were built in such a way that they work together, okay? And that was a conscious effort by the students doing that work to get their stuff to actually work together. And in particular, if you're doing something up at this part of the system, if you're able to make it play well with Spark, all of a sudden, those 250,000 people that are willing to, go to Spark meetups, as well as, the millions of other people that are actually, using Spark, all of a sudden could be interested in your software. So it's a really good way to get a user group very, very quickly. Okay? So that's what we built. And I'm going to talk about a couple pieces of it just to give you a feel for it. So of course, I think I'm going to start with Spark. So if you think back to that first picture I showed, which had this explosion of systems for doing all sorts of things, I talked about why that's problematic for people who really want to do big data analytics. And the idea there was, everybody said, hey, I like MapReduce. I love this idea of being able to scale out so that when I get more data, I add a few more machines, I add some more disks, and the system just grows to accommodate that new load. But MapReduce doesn't do exactly what I want. So what I want to do is I want to build a MapReduce system for graphs, or I want to build a MapReduce system for answering relational database queries. Okay? And when you do that, you end up with that problem that I was talking about, was you get all these individual systems, none of which solves your entire problem, and none of which were really meant to work together. So the insight behind Spark was to say, well, instead of specializing MapReduce, instead of saying, hey, I want to take MapReduce and kind of move it that way, instead, why don't you just grow MapReduce? Why don't you just generalize it, make it support more things than it used to, and then see if you can support all those different use cases. So that's kind of the key idea. The thing that got Spark off the ground was that story I told you about iterative machine learning. But what really made it take off was this idea that you could do more than just any one way of getting at the data in the same system. So we're going to generalize MapReduce. And if you do that, you can plug in all these different modalities into that substrate. Okay? And so what do you have to do to generalize MapReduce? It turns out there's two things. The first one is you need to be able to do more than map and reduce. Okay? And then that way, you've increased the expressiveness of the system. And the second thing you need to do is you got to fix that problem that I talked about, where the original Hadoop MapReduce wasn't able to effectively manage the memory of the cluster in a complex programming environment. Okay? So you want to allow different parts of a complex program to share data that they've already brought into memory and staged there. Okay? And if you could solve those, then if you could do that, then you're not moving data from disk to memory to a different machine and so on. And remember, if you're talking about big data, the last thing you want to do with big data is move it, because it's big, right? So you'd like to keep it where it is and send the processing there. If you can support this sharing of materialized data in memory across different parts of the program, that's how you do it. So those two changes to MapReduce is what Spark brought to the table. Okay, so how did it do it? The original abstraction was something called Resilient Distributed Data Sets, RDDs. And basically, it's just an abstraction of the cluster, so that you take a collection of objects and you spread it across the cluster. But you don't really have to worry as a programmer where it is. So you have a cluster. You have a collection. You know it's distributed, but you don't worry about the actual where the different pieces are. Okay. Now I'm not going to go into this in a lot of detail, but one of the things you give up when you move from Hadoop MapReduce, which is storing everything on disk constantly, to an environment where you're not doing that so much, is you got to worry about what happens when a machine fails, right? Because you got this big cluster, you're running large jobs. The probability of any one machine failing in the middle of a job is pretty high, especially if you're not using the best managed systems out in the world. And so you need to be able to tolerate a partial failure during an execution. And so if you're not going to be writing things out to disk all the time, you need a way to solve that. And the way that RDDs help you solve that is that the interface to them is restricted. And it's restricted in two ways. And I should probably write this in the opposite order. The first thing is that they're immutable, okay? Which means you can't change them. So you create an RDD, you can't go in and change one piece of an RDD, right? You create the RDD, you spread it across the machine, that's what you've got. Then what you can do is you can apply these coarse-grained transformations to an RDD to create a new RDD, okay? Which again is going to be immutable. So you can't go in and do a point update on an RDD But you could take an RDD, you can apply a transformation or a sequence of transformations to it, and get a new RDD out the other side, okay? It turns out that this very restricted environment, this very restricted API is rich enough to let you do a bunch of those things that people were doing in that big collection of software. You know, graphs, queries, machine learning, streaming, you know, all these types of different ways of getting at the data, okay? So that was kind of the big aha of Spark, was that this simple API was rich enough to implement all these different things, all right? So what do we mean by allowing it to do more? So, you know, if you look at the operators that you can apply, these transformations you can apply to RDDs, you got map, you got reduce, so you can do MapReduce, and anything you do with MapReduce you can do here. Plus, you've got all these great things. You can see Jaga's feeling much more comfortable now because there's joins, there's group bys, you know, we even got outer joins, you know, left and right, you know. So you know, the things that of course you want to do to collections of data. You don't want to just map and reduce them. You want to do all these other things. So that's what we mean by expanding the functionality. On the fault tolerance side, the idea is we're going to use this trick of logical logging. So you know, we're not writing the data out to you know, we're not writing the data out to disk after every iteration, and so you need to be able to keep track of what needs to be rebuilt if you lose a machine with its memory contents, right? You need to be able to rebuild what was ever on that machine. And so this is where the immutability comes in. Because now you've got an RDD, you've created it, you've spread it across the machines, you have a map of where all the pieces are. And you know that that it's binary. Either you have this piece of the RDD, in which case you've got it exactly what you need, or you don't have it, in which case you have to figure out how to rebuild it. But you don't have to worry about if you've got a piece of an RDD sitting on your system. You don't have to worry about, gee, is it before or after that update? Because you can't update them, okay? So when you put that together with the simplified interface, you end up being able to do stuff like this. So here's operations on RDDs where you read in a file, you apply this filter transformation to it, and then you apply a map transformation to that. And then what you could do is you could basically treat that as the lineage for any piece of this output RDD. So basically, you know, I created an RDD by reading in a file from HDFS. I then applied a filter to it, and I got this RDD. Then I applied this map operation to it, and I get that RDD. And that gives you a recipe to recreate this guy if you need to. Okay, and that's kind of how Spark addressed this fault tolerance without having to constantly be writing things out to disk for every, you know, in between every operation. Okay, so those are kind of the big ideas behind Spark initially. Where it's gone is people have realized that while some programmers like the low-level abstraction of RDDs, it is fairly low level, and so in most environments, people actually would prefer to write SQL, believe it or not. Or if you're familiar with languages like R or Pandas or, you know, some statistical language, they have another, so SQL works on these things called tables, right, which are sequences of rows. Statistical languages work on these things called DataFrames, which are basically, you know, matrices of data. If you squint, they're really not that much different. So Spark introduced this idea of a data frame, or incorporated this idea of a data frame, I should say, where you could do things like this. So this is a join between, you know, employees and departments, the same thing you'd do with SQL. But it's written in this somewhat imperative-looking way, which is more comfortable for some people. Other people might want to write SQL, and the system lets you do that too, okay? So most users these days don't program directly against RDDs. They write either data frames or SQL or something else, and then that gets translated by a compiler into operations on RDDs. So the compiler has in it this thing called the Catalyst Optimizer. And the Catalyst Optimizer is an interesting thing. So for those of you who know about database query optimization, typically you have a bunch of rules that you want to implement that say things like, well, if I have a query that's doing a join on one relation plus another relation that's got a selection on it, then no matter how I wrote that query, I want to do the selection first and then do the join, because that's going to be less work in the long run. And a bunch of rules like that. And so what Catalyst does is it's got built into it a bunch of rules. But it's been written by a handful of people, and it's competing against optimizers, say like by Oracle and companies like that people have been working on 30 years or longer. So how do you catch up? And the way you catch up is you do it in the open source, so that when somebody sees an optimization that they need that doesn't exist yet, they can write it, and they can put it into the system. So it's this extensible query optimizer combined with open source, right, that's going to leverage that community for making the optimizer smarter and smarter as time goes on. And so it's got that. It's got a bunch of things that modern query optimizers do, like remove, it hardly matters, but compilation tricks, to get a lot of the function calls that you normally do inside a query processor, out, so to inline those functions and so on. It's got a nice extension ability to be able to bring in data, from HDFS, but in CSV form, in one of these other formats, from another database via a JDBC interface, right? And you could keep adding these extenders. And it's got support for user-defined types. So the whole idea behind the optimizer is extensibility. And that's not particularly new, but I think what is new is the combination of that with open source, so that it's not just a small cobble of people sitting in a basement in Redwood City or something, but it's really people around the whole world can add to the optimizer if they want to. OK, great. So how does it work? Well, if you program with RDDs, and this is like some aggregation query where you just got a bunch of data and you're computing some summary statistic on it. RDDs, in this environment, if you use the Python interface, which a lot of people like, it takes this long. If you do it with Scala, it'll go faster. If you do it with SQL using this DataFrame package that comes with the Catalyst optimizer, we can play optimization tricks to make it run faster that you wouldn't necessarily know how to do if you're coding it against straight RDDs. Okay, so that's interesting. That's not super interesting. So the question is, I don't like SQL, I like R. Or I don't even like R, I just want to write Python. Or actually, I really do like Scala. What kind of performance do you get there if you use DataFrames? And this is the fun thing, is you kind of get the same performance no matter which of those interfaces you use. Okay? So why is that? Because what's happening is we're taking the data frame, or they're taking the data frame code, compiling it into an internal representation, and then running that internal representation through the optimizer. And so as long as you get to the same internal representation, you're going to end up with a plan that's very similar, and it's going to run at about the same speed. So it gives you like this flexibility that I had never seen in a database system before, where you get the same performance regardless of which of the interface languages you want to go at the data with. So that's actually a big step forward too. All right, I want to say briefly a couple other techniques that we use. Approximation is one. So when you've got big data, even if you have a linear algorithm, it takes a long time to go through all the data. So if you want to go faster than that, you got to do something sublinear. One way of doing something sublinear is to do sampling and then run on that smaller set of data. So you're still linear, but you get it going much faster. BDAS does that really in two ways. One is a system called BlinkDB, which is Barzan said is Barzan still here? He might have left. Oh, hey, Barzan. So Barzan worked on this, where what you do is you take a sample of the data, you run queries on the sample, and then you give the answer back with a confidence interval, right? And so it goes a lot faster, and you learn about how accurate your answer is. Okay, and you can trade off accuracy versus, or at least confidence versus time. So that's one way. The other way is in the sample clean part of the system, where we take that same insight, but we use it for data cleaning. So the idea is, if I wanted to go through all the records in my database and check them to see if they're accurate and then fix them if they're not, that's going to be super expensive. It's probably going to involve a lot of people. People are slow, people are expensive, people make mistakes. So instead, what we're going to do is we're going to play that same trick, and we're going to take a sample of the data. We're going to clean that sample. And then you've got two ways to go. the first thing you can do is just run the query on that clean sample, okay, in which case, and get error bars, in which case you're basically running BlinkDB, but you're doing it on data that you're pretty sure is clean, right, is higher quality. But if you don't like that, if you don't like that sampling error, you can then run the query on the dirty database and then use what you learned by cleaning that sample as a correcting, as kind of a, it's like what they did with the Hubble telescope when they found out it wasn't working properly. They built a little correction lens and they set somebody up on the space shuttle to put that in the telescope. It's kind of the same thing here. You build this little correction lens and you put that on the answer of your query that you got over the dirty data and get a better answer that way. So it's just kind of two places where approximation comes into the stack. All right, good. Say just briefly, one thing that, as I mentioned, when the Rad Lab started, I was off, like a bunch of other database people, working on this idea of stream processing, where instead of storing the data and then running queries on it, you would run the query incrementally as the data is coming in. We thought that was a good idea. Industry wasn't quite ready for it, I don't think. But now, if you look, people are getting excited about stream processing again. And there's all these systems coming out now around stream processing. You know, things like Storm and Flink and Google. Actually, we have to update this. There's this thing called Apache Beam now that Google released. And then sort of at a little lower level, there's a bunch of interesting projects around reliable messaging. You put these together to build these kind of streaming applications. What does the BDAS stack have to say about that? Well, the way people were talking about doing it, this is, you know, I'm kind of repeating myself. There was this thing called the Lambda Architecture that was, you know, kind of developed to solve this problem. And basically, the Lambda Architecture said, I've got systems like Storm that I can kind of pipe data through and get instantaneous answers on that data. And I've got systems like Spark or Hadoop MapReduce that I can sort of store the data and then run big programs on it and get answers that way. But if I want to get answers that combine the latest real-time data with the data I can get from the answers I can get from the batch system, what I'm going to do is I'm going to glue those together. So I'm going to take, when data comes in, I'm going to stick it in the batch system. I'm going to run it through the speed layer, through the stream processor. I'm going to write my queries twice, right? Once for batch, once for this streaming system. And then when I get answers coming out, I'm going to stitch them back together to produce those answers, okay? And that's what you have to do if you don't have a system that can do both batch and streaming, okay? But if you do it, it's got all the problems that you'd expect, right? You've got two systems that were never meant to work together. They've got different semantics. They're on different revision cycles. They have different bugs. When you write your query twice, you have to figure out, did I write it the same way here as I wrote it here? If you wrote a bug into your query, you got to debug it here, you got to debug it there. It's not a happy situation. So a lot of people now are realizing that really what you want to do is build a system that does both streaming and batch. And you know, as you can imagine, I wouldn't be talking about it if that's not what, you know, if we didn't do that. So of course that's what we did. So the way it was done in Spark was to basically say, okay, we have this ability to take an RDD, which is a collection of data, and process it. If we take a stream, and this was actually not an insight due to Spark. If you look back at the streaming database literature that I was talking about, you know, people, in particular Jennifer Whittam and her group at Stanford, you know, said very early, if you want to understand the semantics of a streaming system, think of the stream as a table that's just being kind of continuously appended to. And at any time, you can take a snapshot of that table and get an answer, okay? And then you understand the semantics of a streaming query. So that's kind of what's being done here is you take the stream and you break it into these mini RDDs, and then you apply your Spark program to each of those little RDDs. And by doing that, you can get this kind of streaming real-time behavior. It's not record at a time, but it goes you know, pretty fast. You can get sub-second response times in this type of a system. And the advantage of doing it this way is you can then, you can then take a program, say like this, which is a program you wrote for your batch system that says, hey, I want to read in this log file, and then I want to calculate something on it. I forget what we're calculating here. You're figuring out for given actions how many times they happen within a 1 hour interval. Okay, and you're doing that over data that you've stored. And if you said, hey, I'd really like to do that over data as it's coming in, then you basically write the same code, except instead of reading a file, you read a stream. And instead of writing out to a file, you write out to a stream. But if you look at this, and you don't have to look at it closely, it's the same code other than that. Okay, so you remove this Lambda architecture problem of having two different systems. All right, good. What I wanted to say about the stack was really graduate student code, combination of people from across a pretty wide set of sub-areas of computer science working together to build this thing. And I talked about Spark in terms of scale-out processing with fault tolerance, talked a little bit about how SQL and streaming work. And what I didn't talk about, because I don't really have too much to say about it, was we also had another set of projects that had to do with trying to make machine learning easier to use. And so the insight basically was that just the way you write a SQL query and the system compiles it into a plan that gets run on the machine, can we do that for machine learning? So can we state at a very high level what we'd like to predict over what kind of data set, and then have the system compile the program that's going to do that prediction for you. And the thing I was going to talk about was something called Keystone ML, which is basically a pipeline system for doing machine learning, where you take multiple machine learning operators, you stitch them together, and then you do the kinds of optimizations that you think you might want to do based on what we've learned from database systems. So you can write and say, hey, I want a linear solver here, and Keystone ML can figure out which of the 6 linear solvers that exist in Spark MLlib is the right one to use for the data set that you have. Okay? Or you could say, hey, I've got this set of operations I want to do, and Keystone ML can figure out, oh, well, if you order the operations this way, you'll get the right answer, and you can compute this thing once instead of twice, and you can keep it in memory and have everyone access it. So doing those kind of pipeline level optimizations, or sort of multiple operator optimizations. Okay, so that's what I wanted to say about the BDAS stack. I want to say just something briefly about people. The idea was, if you look at where the people part of the system, people part of the project is, really we realized there were all these different ways that people were going to be involved in analytics. And so the obvious one is you need to serve predictions and answers to people. We had thought very early in the project that we'd do these kinds of citizen science things where we ask people to go out and find data for us. So that's another thing. You can have people collect data for you. I talked a little bit about sample clean, where you take a sample of the data, you give it to the crowd, and ask the crowd to clean it. So you can actually have people do sophisticated operations on the data to make it better. And then there are data scientists who are writing programs that are going to then do, make these predictions and so on. And so, part of the project was really supporting all these different ways of people interacting with the system. And what we built a bunch of things. Where it kind of ended up from a systems point of view is we're building this thing called AMPCrowd, which basically tries to take systems insights and, to the extent possible, apply them to crowd workers, so that you can take data that you're getting from a live Spark system and integrate that with data that you're getting from an engine like Mechanical Turk. And I don't want to go into it too much, because I want to get to a couple other things. But I guess the key things to notice is there'd been a bunch of work in the crowdsourcing literature about how do you do real-time crowdsourcing. Right? Because the problem is, you send a job to Mechanical Turk, response time is measured in minutes or hours or days. And that's just not going to be sufficient for a lot of analytics applications. And so there'd been a bunch of work on keeping pools of workers kind of on retainer, so that when you ask them a question, they give you an answer right away. So it's sometimes called real-time crowdsourcing. And so we took some of those techniques, and then we extended them to do a couple things. One is we took a page from kind of the Hadoop-style notebook, where what happens is when you spread a job off of, across a bunch of machines, the time to completion of a task is basically the time of the slowest machine. So systems like Hadoop do these things called straggler mitigation, where if you notice a node is going slowly, you'll fire up another job, maybe speculatively, and you'll see which one of those finishes first, and you'll take that answer. And so you can do that with the crowd. So we did that, and we showed it works really well. You can get much faster answers, and you have to pay only a little bit more than you would have paid previously. We also do things like monitor workers and try to figure out which jobs they're good at and which jobs they're not good at, and so on. But the basic idea was to try to build, and then we incorporated a bunch of active learning stuff, some of the stuff that Barzan figured out, and then built that in with other ways of scheduling tasks to improve quality and to get faster answers. So really all I want to say about AMPCrowd is that you can take a systems approach to crowd work, and some of those insights carry over from systems, and some of them don't in some pretty surprising ways. So Dave Patterson wrote this article a couple years ago in CACM called How to Build a Bad Research Center. And the idea was to say, here's a bunch of things you shouldn't do to build a database. So if you do the opposite of what he says in this article, then you'll build a better research center. So AMPLab followed a lot of these rules, the RadLab before it, and so on. And this article is, if you haven't seen it, it talks about this evolution of this model. So one of the things that you're supposed to do that we did is you build a cross-disciplinary team. You try to get people who wouldn't normally work together to work together. And one of the ways you do that is to actually physically put them in the same place, right? So the AMPLab and the RadLab before it was really a big room. I think I have some pictures. It was a big room with a bunch of cubicles or even desks, like you might see at Facebook or Google, some open office. Bunch of meeting rooms, not enough, as some of you guys who spent time in the RadLab know. But the interesting thing is when we started the project, and these are just some random pictures of things that would happen in the lab. We'd use it to have our industry visitors. This is just a really horrible, funny picture of people with cables. We did play, what is that? Space Invaders, thank you. Yeah, we actually did have Space Invaders running. So, but the interesting thing is at the very beginning of the project, you'll notice that this area here was where the faculty sat. So in the early days of the AMPLab, there were a group of, I think there were 6 to 8 of us, who basically gave up our offices and moved into the lab with, all the students and postdocs and researchers, also in the lab. And that was in the very early days, how we collaborated. And it allowed us to move really quickly and to build it. You might be wondering, I showed you that stack with all those white boxes and said each of those boxes was somebody's Ph.D. project. You might wonder, how could you actually ever get all that stuff to work together? And a big part of it is the fact that people were constantly talking to each other to try to make sure that things fit together. It's an interesting idea. Eventually, a lot of the faculty said, boy, I really like having an office. They kind of migrated, but at the beginning of the project, it helped a lot. I already talked about this one, engage industry and foster a community. So we would do things, and again, this was started by the students. We started something called AMPCamp, which was a set of tutorials that we would run for industry people, for our sponsors, and really anybody else who wanted to come. We'd webcast them, so some of them had thousands of people joining in. And it's kind of a funny story. The student who wanted to start AMPCamp was this guy, Andy Konwinski. And he came to me and he said, hey, I want to do a tutorial, and it'd be 2 days, we'd invite a few hundred people. And I said, boy, that sounds like a lot of work. I don't think we should do that. And he said, oh, but listen, we're going to call it AMPCamp. And I was like, okay, we got to do it. So that's how AMPCamp started, and we ran 7 or 8 of these. Eventually, a group in China, that's what this picture is. It says, I don't know if you can read it, says, welcome to AMPCamp China. Groups in China started running AMPCamps. And this was a way that we could bring people in and get them to use the software. And the students basically ran these and fostered that community. This was just one thing we did. There was a whole bunch of sort of online stuff that people did as well. So that's another one is, engage the outside world. And then, we talked a lot about the BDAS stack. So that's this idea of building things and really getting people to use them. And then, finally, I guess I'll just end with this, which is the reason this is a retrospective is because when we started the project, we said, OK, we're going to run it for 5 years. And then a year into it, we got a 5-year grant. So we said, OK, we're going to run it for 6 years. But we always knew all along that there was going to be a day when we would say, OK, this project is now ending, or at least winding down. Students working on it, sorry if you didn't finish in time, you got to leave. No, of course the students still working on their PhDs get to finish. But we don't start up any new things on this project. But we figure out who wants to keep working together, bring in some new people, and think about, OK, we just spent 5 years doing that. What do we want to do for the next 5 years? So instead of just kind of having this thing kind of go on and on and on, put in a date at which you're going to reevaluate and try to move into a new direction. And so that was really valuable too. So I think with that, I'm going to stop, and hopefully you have some questions.
It hasn't been easy.
Whoa!
The robot falls, it breaks.